This is the section for lecture notes titled Special Systems. Our objectives are to solve special systems of linear equations in two variables, and also we'd like to classify systems of linear equations and determine the number of solutions. When two lines intersect at a point, there is exactly one solution to that system. Systems with at least one solution are called consistent. Pay mind to the phrase at least. That means more than one solution is also a consistent linear system. When the two lines in a system do not intersect, we call those parallel lines, and there are no ordered pairs that satisfy both equations. So we say that this type of system has no solution. A system that has no solution is an inconsistent system. If two linear equations in a system have the same graph, the graphs are coincident lines, or the same line, then there are infinitely many solutions of the system because every point of one line is also a point of the other. Again, because there is at least one solution, we would say that this too is consistent. Let's look at an example of a system with no solution. The problem starts by saying, what method would you use to solve the following system? You can choose graphing, substitution, or elimination. We're going to look at this system by graphing, and then we'll look using another method. To graph, we like our equations to be in slope-intercept form. We see the first equation already is in slope-intercept form, and we can rewrite the second equation as y equals x plus 2. If we graph both of these lines, we start at the y-intercept. The first equation starts at -1 with a slope of +1 and moves up and to the right or down and to the left. And the second equation starts at +2 with a slope of 1 and moves up and to the right or down and to the left. Because the slopes are the same, the lines will never get closer to each other, and this means they will never intersect. So we selected graphing, we graph the two lines, we see they're parallel. Because they will never intersect, we say this system has no solution. If we look at this same system and use another method, let's say substitution, we can solve it algebraically to see that there's no solution. Because the first equation is already solved for y, we can take x minus 1 and plug it in wherever we see y in the second equation. This gives us our new equation. We can say -x plus, and I'm going to use parentheses to show I'm substituting in place of y, x minus 1 equals 2. Now we can take the parentheses away if there's nothing to be distributed or multiplied through. And when we combine the first two terms, -x and +x, we see that they cancel. This leaves us with -1 equals 2, which is a false statement. And it will always be false. So if the variables cancel and you're left with a false statement, there is no solution. So here is a different type of system, and this system will have infinitely many solutions to it. Again, we will explore by graphing at first. And we see that the first equation is already in slope-intercept form. Also known as y equals form. The second equation, if we simply move y to the other side, we have 2x plus 1 equals y. That is slope-intercept form. And we see that these two slope-intercept forms are the same. That means both equations have the same graph. And since this system has two lines that are one and the same, that means that every point on the line is an intersection point, and we have infinitely many solutions. If you needed to list some solutions, just choose some x values and plug them in and get the y values. So some solutions are, if I plug in -1, we get -2 plus 1 is -1. That is a solution. If I plug in 0, 2 times 0 plus 1 is 1. That is a solution. If I plug in 1, 2 times 1 plus 1 is 3. That is a solution, and so on. Every point on the line belongs to both of these lines. So again, looking at this same problem, we can see that the original system can be rewritten as the system we see below here. And when both equations are expressed in slope-intercept form, we see that the equations are identical, therefore they have the same graph. And this is why only one line is visible in the previous slide. In conclusion, this system has infinitely many solutions. Any point on one line is also a point on the other line. However, if we continue with this problem and we use an algebraic method instead, let's say substitution, we can take the 2x plus 1 that y is equal to and plug it into the y of the second equation. This generates our new equation, which is 2x minus, I'm using parentheses because I'm substituting into the y variable with 2x plus 1. After the y variable, there is a plus 1 and then equals 0. Now we can distribute that negative through the parentheses, and this gives us 2x minus 2x minus 1 plus 1 equals 0. We see that the x terms cancel. We see that -1 and +1 cancel, and we're left with 0 equals 0. This is a true statement, and it's always true. So we say when the variables cancel, and the result is a true statement, the system has infinite solutions. So we've seen a graphing technique and an algebraic technique for solving special systems that either have no solution or infinitely many solutions. So to complete this section, we want to be able to classify our special systems. Consistent systems can either be independent or dependent. Remember, consistent means that it has one or more solutions. An independent system has exactly one solution. The graph of an independent system consists of two intersecting lines. A dependent system has infinitely many solutions. The graph of a dependent system consists of two coincident lines. So when we say intersecting means at a point or at one point. When we say coincidence, that means one is an overlay of the other. So here we have our table, the number of systems, exactly 1. We have two lines with different slopes, and we see that they intersect at exactly 1 point, and we call this consistent and independent. If we have infinite solutions, and the lines have the same slope and the same y-intercept, then we say that this is consistent and dependent because it is the same equation expressed differently. And when there are no solutions, that means that we have the same slope but different y-intercepts, so the lines will never intersect. We say that this is an inconsistent system. So let's use these three phrases to classify the systems that follow. So if we look at number one, we want to determine, does it have infinite solutions, one solution, or no solution, and then we'll be able to classify. So we'll start by distributing in this second equation, negative 2y minus 4 equals x. And I can rearrange this so I can use elimination. So the system, the first equation is x plus 2y equals negative 4. The second equation I can rewrite as negative x minus 2y equals positive 4. And all I did was move the x to the left side of the equal sign and the negative 4 to the right side of the equal sign. And that's how I generated equation 2. And now that it's been rearranged to use elimination, I can add the two equations together. I see that x and negative x cancel. 2y and negative 2y cancel. So we have 0 on the left-hand side. On the right-hand side, negative 4 and positive 4 cancel. 0 equals 0 is a true statement. That means we have infinite solutions. So if we were to classify, we would say this is consistent and dependent. Okay, so let's look at example 2. We'll start by distributing that negative 2 through the first equation. So our system becomes y equals negative 2x plus 2, and the second equation remains y equals negative x plus 3. I can take the y from the top equation, which is negative 2x plus 2, and replace the y in the second equation. This gives us negative 2x plus 2 equals negative x plus 3. Let's get all of the x's on one side and the constants on the other side. And we see that x is equal to negative 1. This is a unique solution, which means that there is one solution. If I plug that negative 1 for x back into both equations, do I get the same y? Well, plug negative 1 into the first equation. We have negative 1 minus 1 is negative 2. Negative 2 times negative 2 is positive 4. And if we plug negative 1 for x in the second equation, the negative of negative 1 is positive 1 plus 3 is positive 4. Because they match, we have one solution, and that is negative 1 comma 4. So this system is consistent and independent. So for the third equation, I see that I have y is equal to 2/3 x. I'm going to use substitution to plug that into the y of the first equation. 2x minus 3 parentheses, because I'm doing a substitution, 2/3 x equals 6. When we cross cancel here, 3 and 3 will cancel out. This leaves with 2x minus 2x equals 6. And we see that 2x minus 2x becomes 0 equals 6. This is a false statement, which means there is no solution, and that this system is inconsistent. That is the end of our lecture notes for section 4. Review this video as needed, take notes and pause. Complete the Section 4 practice. Check your work with the answer key. Once you've satisfied that you're doing the practice problems correctly, go on and complete the Section 4 quiz. This is the last quiz for the course, so once you complete the Section 4 quiz, you've completed the course.